All right. Hello, everyone. Well, it looks like we're maybe on our third live stream, getting a little more used to this. So, well, yeah, welcome. Looks like we have, see how many users we have right now. 4 users. Okay, all right. Looks like we're up, and I think everybody can hear me. The microphone shows that we're transmitting. And yeah, welcome. So for today's topic, we're going to talk about CAN bus and OBDII. And what we're not going to do is go into a deep dive of what CAN bus is all about and how it works. There's plenty of tutorials, both online and in video form. But we're going to, on the technical side, we're going to scrape just the surface of what CAN bus is, just so you can get a sense of what it's all about and how OBDII fits into what CAN bus is, because there's a relationship there. And we'll go through some demos on hooking up and inspecting data, and of course answer your questions. So, okay, so we have a little presentation here. So a good way to think about CAN bus is what it's not. So if you think about sensors and collecting data from different sources, let's say in this example we're collecting stuff from the engine. So what CAN bus is not is it's not individual sensor connections. So traditionally you have one wire going to RPM, another wire going to engine temperature, and so on. So you have all these individual wires going to different sensors, and then those sensor values are read. Like 0 to 5 volts might get mapped to like 0 to 100 psi of oil pressure or whatever. So CAN bus is not that. So what it is a way to stream data from multiple sources all over one cable. So there are some obvious benefits to that. You have a single cable that goes to maybe is chained together between different devices and different sensors, and it all funnels into one connection on the data system. So this is really similar in concept to, like, you have a computer with a network cable plugs into a hub, and you have other computers on the network. So that's a pretty big simplification, but the gist of it is that data from different sources flow over the same cable, and it can get collected to a single source. All right. So with CAN bus, data is sent over a message. So there's these little messages flying around on the CAN bus network, and each message has a little bit of information about it with some extra information describing the message. So here's the technical information about a CAN message. We're not going to dive into that. There's data, there's a CAN ID, and then there's stuff at the beginning and end of the message to help manage that flow of information. So we're not going to really talk about that. What we will talk about is what matters most. So with CAN bus, the thing that matters most to the average person is you have an ID, and that's a number. So the ID of the CAN message identifies like the message itself, and typically maps to, like, this ID comes from an ECU, or another ID might come from a sensor. And then each message has 8 pieces of information in terms of bytes. So we have byte 0 through byte 7. Typically we talk about it being 0 based, so byte 0 is the first byte. And there's these little messages flying around on this network, and you'll have different messages from different sources. Just basically, the system works in a way where they all cooperate, and one message gets onto the network, and then another device will wait for the bus to be available, and then might send another message behind it, and so on. So there are a lot of technical details on how that works. If you want, you can Google that, but it's kind of cool, but it doesn't really matter in this context. So what we're going to do with that message is we're going to pack some stuff into it. So what are we going to pack into it? Well, it could be anything, really. In this case, we're going to be... Thanks. Mitch, I don't think I can teach you anything about CAN bus, though. Just saw a comment from Mitch. Anyways, yeah. So what can we pack into a message? Well, we can pack throttle position, RPM, different sensor values, and each message can contain bits of information from that represent different things. Not a message doesn't just contain one item. So in this completely contrived example, we're using 2 bytes to represent throttle position, another 2 bytes to represent RPM, and then 4 bytes to represent various pressures and temperatures. So the reason why you would use 2 bytes is that if you need extra range to describe the data that you're sending, 1 byte is 0 to 255, and 2 bytes is 16 bits, so you can do 0 to 65535. So those values then get translated into a real-world value, like 0 to 100% for throttle position, 0 to 10,000 RPM for RPM, and so on. Okay, let's do a little demo on how CAN bus works in the context of RaceCapture. So here we're connected to a RaceCapture Pro Mark IV that's sitting here on the bench, and we have what we're going to do is we will have the Tire X sensor connected with some cables, and what we're going to hook up this sensor and read some data from it. So, all right, so we have a blank slate here. Well, first of all, we're going to turn on our CAN channels, and we're going to add a mapping for Tire X. So this Tire X sensor is this is the left front sensor. First thing I'm going to do is look at the documentation. So the documentation on our site, it's a little more complex than most, because each sensor has the left front and right front, left rear, right rear offset. But the way we've designed it is that we have a base address for the sensor, and then each sensor position has an offset. So it's so the base address for the sensor is 41216, and then so that's A100 hex, 41216, and then we're going to scroll down and find the information for the temperature zones. So offset 0, the offset for 4 zones is that base address 41216 plus 32. So we will go ahead and add that. So that is 41248. So we're going to give this a channel name. Tire left front 1. And we're going to give it a max value of, 100 is fine. And then we're going to say our CAN ID is 41248. And it's going to be connected to CAN bus number 2. And then the raw value mapping. So if you remember in the demo, we had bits of information within the CAN message. So the offset within that. So you see the byte 0 through byte 7 here. So what we do is we say the offset is byte 0, and we have each zone as 1 byte. Zone 1 is in 1 byte, zone 2 is in a second byte, and so on. So we go ahead and say offset 0, length 1. We say it's unsigned, and it is Little Indian, if I remember correctly. And then we look at the formula. This is another thing with CAN bus. We say the formula is a divided by 2, or we could say times 0.5. We also have a divider, so we could say divide by 2. We almost didn't include the divider, but people said, well, it's an additional bit of flexibility, so why not? So we added that. Let's see what else we can do. I think that is about it. And then let's set the rate to 10 Hertz. And then there is our first channel. So this is zone 1 of the left front tire. So the TireX sensor by default is set to 4 zones. So we would go to add the remaining 3 zones. We would add those 3. So let me pause. I have a question here. Your screen is split in such a way we can't see the window from the software correctly. I apologize for that. Aha, there we go. Thank you for calling that out. Okay. All right, let's go ahead, and what we'll do is we will write this and go to our dashboard, and let's see if we see some data. So I'm going to hook up TireX to RaceCapture. So I'm going to plug things in. And then we're going to plug this into the B port via a terminating resistor. And we have the TireX sensor plugged in as well. And okay, so the orange LED is flashing on the RaceCapture Pro. And oh, there we go. So on the screen, you should see that the inside zone of the TireX sensor is updating with information as I wave my hand over it. Get some, there we go. All right. So to save some time, what I'm going to do is select a preset, and I'm going to just import the preset from RaceCapture and overwrite it. And then that just brings in all of the channels for that sensor. If I write the data, then I go back, and then now we see all the data for those 4 zones for that sensor that is connected. So if we go back to setup and look at edit our channel again, a few things just to recap the things you can do. You can edit the name of the channel and set the units. You can set the digits of precision for logging, so how many digits pass on the right side of the decimal point. You could set a min value and you could set a min value and a max value. You can specify the CAN ID, which we covered. There's a concept called sub ID, which is not often used, but it's a way of using the first byte of the CAN message to act as like a sub ID. So you have the ID and the first byte of the message it matches on, and then it would match to that message and then be used to map the data. So this is typically, you'll know when you need to use this. So in almost all cases, you can ignore this one. You can select the CAN bus 1 or 2. You can specify an ID mask, which is an advanced feature you'll see in our wiki documentation. Usually you don't need this almost all the time. The raw value mapping, we have the concept of bit mode. So if things are not organized in even byte increments, then you can specify a bit offset within the CAN bus message and then a customized length. Fortunately, in a lot of cases, except with a lot of OEM CAN bus networks, like third-party manufacturers of sensors and everything, they typically just do things in whole bytes, and it makes it a little bit easier. So for the source type, this is the type of data that's encoded in the CAN bus message. So it could be like a raw unsigned value. So unsigned means it doesn't go negative, of course. Signed it could be a negative or positive value. A float value means it could be like a floating point number that's encoded into the data. Sign magnitude is almost only seen with steering angle sensors. Like this was added when we were first decoding the BMW E46 CAN bus, and it's a way of specifying, like, it's like an unsigned number with a sign bit that's like done differently than like your typical signed value. And then of course the formula, which turns the raw value into a real world value. And then finally we have a units conversion. So if your formula is specified in like Celsius, like from the manufacturer, you don't have to like try to figure out how to turn that into Fahrenheit via the formula. You can go in here, the formula can specify like Celsius. If you want to go to Fahrenheit, you can select this Celsius to Fahrenheit, and then on the fly it'll convert it to the units that you prefer. By default, it is no conversion. Cool. All right, let me see if there's any questions. All right. Yeah, thanks, Ray, for pointing that out. I would have just kept going with the window off the screen. So it looks like I left part of the window obscured because of the live stream I did with Scott Barton last time. So yeah, this is first time early streamers teething problems. All right. Another little feature that we have added that will be available in the next version of the app, the 2.5.0, is that we have, in addition, so we have our own presets, which you can browse system provided presets, you have your own presets, and then you have shared presets from other users you can import, and these are pulled from the cloud. So it looks like we have nice. That's a nice preview message. Tire Magic external TPMS, and then some other presets that people have shared, which is cool. It's cool to see people doing that. So aside from that, what you can do is you can import a DBC file with version 2.5.0, which will be coming out soon. We thought it was going to be last week, and it didn't happen, but it's going to have a lot of great features, including the ability to import a DBC file. When you select a DBC file, it'll ask if you need to override or not, but first it will give you a little message. It says, make sure to check the unit sample rate formula. It's just a little advisory. It says, like, when you import a DBC, there will be other things you need to check because a DBC file doesn't have exactly everything that we support in our CAN mapping. Here it says, okay, overwrite or append existing channels. So we'll overwrite. And when you import a DBC, it just selects a default sample rate of 10 Hertz. And then with like no unit, so you can go in there and adjust it. But this is a quick way to get started with importing a DBC versus just doing it by hand. So a really important thing to understand regarding the sample rate, since CAN bus is streaming, it's pushing data to RaceCapture at the rate that the source system determines, right? So if the source system, like the ECU, sends something out once per second, RaceCapture will receive that, and then the sample rate that you define here is how frequent we report the current value that we have. Since we have no way of controlling how fast the data comes from the other system, you can it's like a way of upsampling or downsampling. So if you if stuff is coming like at a very high rate, but you only need to just have it show up in the logs like once per second, the source system could be sending at 100 hertz, but you said I only want to report it at every 1 second. So then you could say just report at 1 hertz. So we have a question from Mitch. Is offset from the absolute leftmost bit, or does it follow a little Indian standard, much like the DBC file information? That's a good question. So it is from the, I think, so a recent bug fix that we did, I think it follows the little Indian standard. It's not in an absolute way. But that was a recent bug fix that we had in our firmware, which was kind of a brain bender. But yeah, we could follow up offline on that. That's an excellent question. Okay. I think I've covered, I'm trying to think of what else that would matter in terms of mapping CAN bus data. Yeah, so importing a DBC, browsing presets. There are a lot of people doing reverse engineering of their own vehicle. Like we have some blog posts on that, and there's lots of online resources about how to reverse engineer CAN bus protocols. If you have figured that out for your car, or if you have information for a device, let us know. Just drop us an email. If you reverse engineered your own car, then we will feature you as one of our presets. So these are all any of our presets that have cars featured are ones from, these are actually the actual customers that did the work. So we feature them in our presets. So it's a little thing, but it's fun. So yeah, we have a blog post with Chris Wynn. We jacked up his car and decoded, just inspected the CAN bus data coming from his car, jacked up his car, spun the wheels, turned the steering wheel, ran the engine, and watched the data change. That was a pretty fun exercise. So, okay. So the next thing we'll talk about is OBDII. So there's a lot of confusion around what OBDII is and isn't. And make sure that everybody can see that. Okay, so OBDII is, there is a relationship to CAN bus with OBDII, but it's more like the way the medium that OBDII operates on top of. So the metaphor is like if you were to have a conversation over a phone line, the phone line is CAN bus, the conversation is OBDII. And with OBDII, it's a request-reply protocol. So over this conversation, the data system, RaceCapture, will say, hey, ECU, send me the RPM. And then the ECU does the stuff to get the RPM. And then the ECU replies back and says, okay, here's the RPM. And then RaceCapture goes, okay, now send me the throttle position. And then it goes ping pong back and forth like that. So the thing to understand with OBDII, it is a request reply protocol, and you can only request one thing at a time. So with CAN bus, if we go back to the CAN bus messages, the data it's like a fire hose of data from the source system. So each message could have a number of bits of information like throttle position, RPM. Multiple things could be sent seemingly in parallel. Of course, messages are arriving one at a time, but it feels like it's in parallel, and it has the effect of parallel data reception from those source systems. With OBDII, it is one request at a time. So because of that, OBDII is also kind of slow. So modern OBDII systems uses CAN bus for that conversation. CAN bus is pretty fast. So let's say you hook up, you configure RPM and you set it to like 50 hertz, and it's like the only channel you have set up. That request reply is happening really fast, right? So it feels responsive. Then again, if you load up a whole bunch of OBD2 channels, each of those requests happens one at a time. RaceCapture has some optimization techniques based on the sample rate you've chosen, but we do our best to make OBD2 as fast as possible. So it can be reasonably fast, like very useful for data analysis. But you still want to conserve like how many channels you use. Now the thing is, and this was this reminds me of a recent conversation in our community. But one of our customers was saying like, oh man, it's like really laggy, like, and they thought it was like the wireless interface. But we found out that it was the legacy OBD2 protocol that they were using. So the way to tell was like, all right, like RaceCapture has a built-in yaw sensor that reports at 25 hertz by default. So like if you were to move the RaceCapture, you would see that like the yaw sensor on the dashboard updates quickly. But the data coming from the legacy OBD2 interface is slow, and it only updates as fast as that legacy interface will allow. And what I mean by the legacy interface is that prior to 2008, vehicle manufacturers used a variety of different protocols like electrical standards and signaling protocols to act as a way to retrieve data, like for emissions purposes. And to do emissions on a vehicle, you don't need a high performance interface. It's a scan tool. That's all it is. It's not for like motorsports data acquisition. But still, people will try to do what they can with those interfaces. And we do have a device called our legacy adapter that converts that old style protocol to CAN bus that RaceCapture can understand. And then RaceCapture, it's basically a translation layer. So RaceCapture thinks it's talking to a CAN bus equipped vehicle, but it's just slower. So what happens is that like RaceCapture requests that bit of information, and then the car takes a long time to reply, and then it comes back. So some legacy interfaces are faster than others. Some are excruciatingly slow. Like my E36 M3 has the which like the late 90s like German cars would use this ISO protocol that was especially slow. And if I just have like RPM set up and the only channel, I might get like 10 hertz out of it. So okay, but yeah, so that's the story with OBD2. It's a request reply protocol that sits on top of a signaling infrastructure like CAN bus or these legacy protocols, I mean. And that's how it works. So with OBD2, we have the SAE standard PIDs. So if we go to RaceCapture's OBD2 interface under setup, we want to make sure we turn that on, and then we have import an OBD2 preset, and then we have a preset that is what we call our essentials OBD2 channels. So we select that, and then that brings in engine temp, RPM, throttle position as a kind of like a starter set of channels that like these three like almost always work. So OBD2, like the SAE, the government mandates that that if let me see if I get this right. they said if you're going to support these channels, it has to appear in this way, which is why you can say OBD2 works the same across different vehicles. But not all vehicles support all channels. So, and it really depends on what the nature of the engine and what it supports. So like a good example would be like an engine may have a manifold pressure sensor, but some do not. So manifold pressure might show up on some OBD2 interfaces and may not show up on others. So, but like RPM is virtually like throttle position, RPM, and engine temperature. You can almost always count on those. So if you edit an OBD2 channel, you have this concept called a PID. And PID stands for, somebody correct me if I'm wrong, I believe it stands for parameter ID. And there is a number for this value. And each channel type, and there's a good Wikipedia for OBD2 PIDs that you can go and find these, but in the case of RPM, the PID for RPM is 12. And then a lot of the rest of these tabs should be very familiar because it behaves exactly in the same way as a CAN bus mapping. So in almost all cases, the data comes back under CAN ID 2024, and then there's a raw value mapping. So in the case of RPM, the offset is 3 and the length is 2. So it's 2 bytes of RPM data. And then the value is, the RPM data is, you multiply it by 1 and divide it by 4. And that's how it works for the OBD2 mapping. So with engine temperature, the PID is 5. The CAN ID is still 2024 because it's that request reply. And then the raw value mapping is, we have an offset of 3, the length of 1. And then the formula is, it's just the value times 1 divided by 1 and then an offset of 40. So subtract 40 from that so that the temperature can read down to negative 40 Celsius. So yeah. So that's how OBD2 channels work. So one thing to note is that OBD2 and CAN mapping can work simultaneously on RaceCapture. And even if the OBD2 channel is on the same CAN bus. So by default, we have OBD2 operates off of CAN bus number 1 because that's CAN bus 1 is the same connection that for power and CAN bus that we use. So it's a single wire connection to the OBD2 port, or if you have it hardwired. So OBD2 is by default on CAN 1. And the OBD2 engine within RaceCapture will do that request reply, and it does it as fast as the ECU allows, which has gotten us into trouble on certain vehicles. There's a way to slow that down, but basically we just, as soon as we get the response, we put out the next request. While the OBD2 engine is running, the CAN mapping subsystem can still work and map data. If it sees data that's coming across the CAN bus, whether it's on CAN 1 or CAN 2, it will just map that into channels and it'll work. So both can work simultaneously. And there are a lot of cases where some data is available through direct CAN mapping. Like let's say your ECU is broadcasting some data that you've reverse engineered. You can, let's say you got everything except RPM. So what you could do is you can have your direct CAN mapping via the CAN mapping here, and then you can say, okay, I'm just gonna have RPM over OBD2, and then they can happily coexist. Yeah, so we have one last topic, and we have the concept of extended OBD2 PIDs. So with OBD2, you have the federally mandated SAE standard bits of information like RPM or engine temperature or manifold pressure. So if the car has that available, then it will conform to the standard PID. So we could probably bring that up to Wikipedia. So yeah, so here's our OBD2 PIDs, and then this is a good one I've spent a lot of time on here. But So we have engine coolant temperature. This was PID 5, which you saw before. And then here's all the min-max values in the formula. So if a car supports it, it'll use this format. So these formulas and these PIDs, and then the values returned. So yeah, we have the concept of extended OBD2 PIDs. What that means is that OEMs will have OEM-specific information available over OBD2, and this is a way for them to have their own specific proprietary data channels that only pertain to that vehicle. So we just had a customer do this with a Corvette, and they in their case they used the Torque app, which is a great source of information for extended PIDs. So in this screenshot, what you can see is, let's say we have oil pressure. Oil pressure has a PID of 221470. And the way in torque parlance, the 22 means mode 22, and that's set in the RaceCapture software. And then we have the PID, which is the rest of that, which is 1470 hex, and we turn that into decimal. And then there's a formula, which is this equation. So if we go back to RaceCapture, we would do add an OBD2 channel. So we call that oil. And I think we'll just keep the defaults here. We'll select a sample rate. So we said the PID was 5232. And we'll set the mode as 22. And the CAN ID matches, that should be, I don't have that memorized, but I think that's 2420. Anyways, the CAN ID would be the same CAN ID that that you would have with a regular OBD2 query, and then you would have the raw value mapping 0.578. So So if we add, let's say if we add another engine temperature, let's say if we add engine temperature and go back in, we would have PID 5, 2024, and then the raw value mapping is, for a single byte value, it is offset 3 and length 1. So we can go back in and then do offset 3, length 1. And then set that. And if I go back in 2024, and Indian is big. That is something to note with OBD2. The Indian is big, so you have to change that to and then that gets you oil pressure over extended OBD2 PID. So there we are. That is an example of configuring an extended OBD2 channel. Well, I will open it up to final questions. Looks like we're right at the 40-minute mark, which is just optimal. Yeah, this Torque app is pretty handy. So if you have Torque installed, pull up your car, find the channel you want, and then use this guide for configuring a channel. What you can do is you can start with an existing channel, and then like you switch the mode to 22, and then change the raw value mapping and the formula to match that. Okay, well, our goal is to keep these live streams concise so we can do them in high velocity, hopefully on a week cadence or maybe bi-weekly. So yeah, thank you. Yeah, thanks for watching. I hope this was helpful, and ask any questions in our community or on this YouTube video, and we will get to them. And yeah, so we're about at 800 likes right now, and apparently something magical happens at 1,000 likes. But if I shouldn't say likes, but subscriptions. My brain is a little tired today, but yeah, if we are at 800 subscriptions, if we could get a if you like what you see and you want to be notified as soon as possible, give us a subscribe, and you'll get a notification when we have a new video. Okay. Thank you very much. Oh, so Mitch says some of that OBDII PID Wikipedia page is authored by yours truly. That's awesome. Yeah, that is a really useful page for sure. So yeah, thank you for that. All right, everyone. Thanks for watching, and we will see you next time.